We continue our discussion of hydrostatics and we talk about the force on a plane surface exerted by a fluid. Now imagine that you have a tank that is filled with some fluid like water with density rho, and we wish to know what is the force acting on the bottom surface of the tank, as well as what is the force that is acting on the side wall of the tank. Now if you think about it, you are on Earth, so you are going to have some kind of pressure, that is some kind of gravity. That is, if you think about the pressure at this level, at the bottom level, this is at a height that is h below the top surface, and we'll assume that the top surface is exposed to the atmosphere. So the pressure over here is P atmosphere. The pressure at this level, we did this type of calculation in the previous video, is P atmosphere plus rho, or density of the fluid, times G times H. And how is that pressure distributed? It's distributed uniformly because at a given horizontal level the pressure is the same. So it's like a uniformly distributed load whose magnitude is P atmosphere plus rho GH. That is the pressure that is acting on the bottom surface. Now if you wish to compute what is the force, this is the pressure, which you know is force per area. Okay, it's a distributed load per area. Okay, load per area. So what you have here is the pressure at the bottom face is P atmosphere plus rho GH. Now suppose the bottom face, as you know, is rectangular in cross section and has an area of A. We are going to say the force on the bottom face or bottom surface is going to be the pressure at the bottom at that depth multiplied by the area of the bottom. So I'll just write this as P atmosphere plus rho GH times A. Okay. Now if you think of that rectangular area, what you have is a uniform pressure distribution. That is, this load is uniform across the entire face. Okay, so I'm just going to draw arrows everywhere, and what I am trying to convey is that they all have the same length, or they are all of the same force per unit area. So the resultant of this force, that is, if I have all these uniform forces, I can say that if my rectangle is here, the pressure acts at the geometric center, or the resultant force acts at the geometric center or center of mass resultant of pressure distribution. It acts at the center, and its magnitude is equal to P atmosphere plus rho GH times A. Okay, and most often the atmospheric pressure is much smaller than rho GH, that we assume that it's approximately 0. Okay, or if it's a free surface, we just say the atmospheric pressure, we just say the pressure is 0, assuming that there is an atmosphere, and we subtract the effect of it. So the resultant force is compactly written sometimes as rho GH times the area. Okay, now this is for the bottom face. So you have your bottom face. If I draw only the side view, this is the load distribution, which is like a uniform distributed load of magnitude P atmosphere plus rho GH, or simply rho GH, and the resultant force acts at the center, Fr equals rho GH times A. Nice and easy. This is the bottom face where we have the pressure acting on here. Now if you also think about the bottom face also bears the weight of the fluid above it. So the resultant force is going to be rho GH times A plus the density of the fluid times H A, is equal to rho GH over A. You can also think of this as the weight of the fluid rho HA is simply volume times G. So this is mass times G, or the weight that we know of. So you can think of it as both ways. The hydrostatic pressure arises due to gravity, and it can be either thought of as rho GH times A, which is the pressure times area, or the mass times gravity. Okay. Now focusing on the side wall, so here is your tank, here is the top level of the liquid, and we'll say that this free surface has a pressure of 0. We used to call it atmospheric pressure, but we can simply ignore it and say P is 0 at the top surface. And on the side wall, if you think about it, what is going to be the pressure distribution on the side wall? Pressure distribution on the side wall. You do know that the pressure at every horizontal level is the same, that the pressure changes only with height. So if you have P is a function of Z only, height only. So if we say this is Z, okay, this level is Z equals 0, this level equals Z equals H, you can write P of Z. If you don't know how to write this, you can start with the equation dP by dZ equals minus rho G, and then integrate dP from P of Z equals H to the pressure at any height Z equals minus rho G times Z equals H to Z. The pressure at Z equals H equals minus rho G times Z minus H. The pressure at Z equals H, the top surface, we say the pressure is 0. So P of Z is simply minus rho G times Z minus H, or I can write this as rho G times H minus Z, knowing that Z varies only between 0 to H. Okay, so the pressure is going to be 0 at the top, and it's going to be maximum at the bottom, and at the bottom the pressure is equal to rho GH. Okay, it's nice and easy. So what you have here is the side wall, here is the bottom where the pressure is rho GH, here is the top where the pressure is 0, and you have a linear variation of pressure, or a load that is linearly varying with height between the bottom and the top. You have P of Z. P of Z is rho G H minus Z. You want to compute what is the force, the resultant force acting on the side wall, which you can compute as the pressure times a differential area integrated over the entire area. That is, I'm taking a small area dA, and this is the side view. Remember, this is the side view. So if I have the side view here, I'm taking dA. Okay, If I see it from the front, I'm going to have the side wall. Okay, this is the side wall, and my dA, so this is the direction Z. Okay, this direction is Z, and let's say this is the patch. Okay, or this is the patch. This is the patch, and this height is dz, and this is the width perpendicular to the page of the paper that is on which we are writing. So w is the width perpendicular to the plane of the paper. So I can write dA equals w dz. The differential area is the width multiplied by the differential height. Okay, so I have the force, the resultant force, being an integral of P of z times w times dz, and z is going to vary obviously between 0 to h. So I have rho g h minus z w dz integrated from 0 to h. Okay, so I have rho g w, I have h times h minus 0 minus h squared over 2. Okay, so what do I have here? I have rho g w h squared over 2. This is the resultant force, the magnitude of the resultant. So if I have a side wall and I have a pressure distribution, that is a distributed load, 0 rho g h here, and this is z. This can be replaced with a single resultant force, Fr, whose magnitude is rho g h squared over 2 times w. Now the only question is, where is this resultant going to act? Where is it going to act? You have a distributed load. The larger pressure is near the bottom, the smaller pressures are near the top, which means the resultant must be closer to the bottom, which is the region of higher pressure, than the top, which is the region of lower pressure. So you need to account for the fact that the resultant is weighted by where the pressure is higher. Okay, and you can do this simply by considering the fact that if you have a resultant, and you have a distributed load, okay, the resultant is such that it will produce the same moment as well as force as the distributed load. Fr is the force equivalent to the distributed load and also leads to the same moment as the distributed load. It leads to the same moment as the distributed load. Now we use this part of the definition to evaluate what is the magnitude of Fr. We can use the second part to evaluate where should Fr act. And now suppose I consider the bottom, which is z equals 0, and I say that Fr acts at a distance, Fr acts at a height that is ZR from the bottom. The resultant acts at a height ZR from the bottom. So the moment about the, I'll call this point O. The moment about the point O is YR times FR, or YR times rho g h squared over 2 times W. Okay. I can also calculate what is the moment about O by writing integral P of Z times W dA, W dZ times Z. This Z is the moment arm. Okay, that is if I take this point here Z equals 0, if I take P of Z to be at an arbitrary height Z, okay, this is the moment arm. So P of Z times W dZ is the force times Z is the moment arm, and this needs to be integrated from Z equals 0 to H. So if I do that, I have 0 to H, rho G H minus Z times W dZ times Z. Or if I write this, rho G W times 0 to H, HZ minus Z squared dZ. So I have rho G W H squared over 2 minus H cube over 3. Or this is rho G W H cube. I have 1 half minus 1/3, which is what? Which is 1/6. Which is 1/6. 1 half minus 1/3. That's right. So I have YR times rho G H squared over 2 times W equals rho G W H cube over 6. So if I solve for YR, this is equal to H over 3, or in other words, the resultant acts 1/3 of the height, or 1/3 of the height of the top height of the fluid level from the bottom. Okay, so I can write this pressure distribution, which is rho G H and linearly decreases, is equivalent to a single force YR or FR, which is rho G H squared over 2 times W, acting at a distance H over 3 from the bottom. You can also say this is 2/3 of the H from the top. You can do the same calculation. You can do the same calculation by considering the moment about the top point, and you will arrive at the exact same result. Okay. Now that is an example of trying to calculate the resultant force due to on a plane surface due to hydrostatic pressure. Okay. Now we want to do this for a variety of conditions or variety of situations, and the next step is to derive some general formulas that will be applicable for any surface at any depth, at any orientation, instead of the very special case that I discussed here of a tank containing water. Okay, we want to make this a little more general. To build a general expression for the force on a submerged surface, we go through the derivation that is described in figure 2.17. What we have is a surface that is beneath a free surface, which is where this is the liquid side and this is the gas side or vacuum or whatever. So you have a liquid and you have a surface that is immersed under the liquid. You do know that the surface is subject to pressure. Like the pressure is always normal. So if you are thinking of what is the direction of the pressure, it's always going to be compressive from both sides. Okay. So what you want to know is that what is the resultant force Fr on this surface, which I'm not assuming it to be a rectangle or a circle or anything. It could be an arbitrary area of A, and we want to know what is the magnitude of the resultant Fr, and then where is the center of pressure, which is another word that is used to denote the location where the resultant force acts. To calculate Fr, you can go through the derivation that is given in section 2.8, but what I'll do is just summarize the equations that we will eventually use, and you might as well put this on your cheat sheet right away, that these are the equations to calculate the resultant force and the location. So this Fr is equal to rho g times hc times A, where hc is the height of the centroid from the free surface. Okay, it's denoted in the figure in the previous slide. hc is the location of the centroid from the free surface. Okay, so if you know the angle at which this surface is submerged, you can locate where is the centroid of that surface, and then using that and the principles of trigonometry, you can simply locate or calculate what is hc, and we'll be doing this through examples as we go on. To locate the center of pressure, okay, we need to define a x coordinate and y coordinate which is relative to the surface. That is, we need to define this. If you have your x and y here, suppose this direction is x and this direction is y, you need to define what is going to be xr and yr relative to these xy coordinate systems. And if you go through the derivation, which I'm not going through because the derivation itself is not important, is equal to Ixc divided by Yc times A plus Yc. And xr, the x coordinate of the center of pressure, is Ixyc divided by Yc times A plus Xc, where Xc and Yc are the coordinates of the centroid. Coordinates of the centroid. Okay. Now, this set of equations here is what you need for solving problems on this topic. That is, we are going to see through examples during lecture how to use these equations. Okay. Now, you may wonder what is Ixc and Ixyc. These are the second moment of area, and to know them, you can simply revise your course notes from the statics course. It's the second moment of area about the x-axis and about the xy axis. And there is also figure 2.18, which lists Ixc and Ixyc for common shapes like rectangle, circle, semicircle, triangle, and a quadrant. These are the shapes that we will cover in this class. That is, all the numerical problems in the homework as well as the exams, they'll be based only on these shapes only. Okay. So along with the equations that I gave in the previous slide, which are equation 2.18, 2.19 and 2.20 from the book, plus figure 2.18 is what you need for computing forces on submerged surfaces. This is really a repeat of statics that you learned in the statics class, and we will see this through examples. Okay, so maybe the equations right away don't make a lot of sense. You will see them in action during the lecture period. That's what we want to do. So with this, we wrap up module 2 or chapter 2 on fluid statics. Please go through homework 2 that has problems that will illustrate these concepts better. And please watch this video before you come to class, so that during class we will use the time to solve numerical problems, and we'll also try to accommodate as many questions as we can based on what you read and what you heard in this lecture. So please go through homework 2. Due date will be listed on there. Okay, and come prepared for class. Okay, thank you.